Hello friends, I am Shubhadeep Shadukha from IIT Kanpur Department of Physics. Today I will talk about diffusion equation and its solution in one-dimensional system. So I will talk about how to solve it in computer, and I will use Python programming. In the first part of this video, I have shown you how to do it with the finite difference method. Today I will talk about the spectral method, and for that I will actually do the this is my previous code, which is actually solving the thing with finite difference method, and next I will do that same thing with spectral method. So let me tell you about this spectral method. Okay, so the spectral method is something that when you write your equation, the diffusion equation in real space, we have seen the form, that is, it is actually involved about the real space derivatives of the unknown variable u. Now if I go to the Fourier space, and I hope all of you know the what is Fourier transform and the other things. So if you just take a Fourier transform of an equation, and you will get the equation in Fourier space, right? So let me just define it like this, that ux and its Fourier transform is u hat k. Okay, so it is in k space. Okay, and in Fourier space the real space derivatives can be evaluated using the property of the Fourier transform of the derivative of the function. So if I know that the Fourier transform of ux is u hat k, then if I just want to compute the Fourier transform of du dx, okay, so du dx, its Fourier transform can be given by, it is given by ik multiplied by u hat k. So it is easy to get the derivative, the space derivative, by just multiplying that ik. This ik, the ddx will be just replaced by ik. So for this case, so this is the double derivative, then it will be just ik multiplied by ik, that will be just minus k square. Okay, so in Fourier space this diffusion equation can be written as this. So okay, and what is the strength of this Fourier transform and the spectral method? Because the space derivatives, this is very sensitive. When you use the finite difference code, then it is very sensitive on the grid choice, like delta x, whatever you have used in your finite difference code, delta x, it is very sensitive to the derivatives. But compared to that, the Fourier derivative, using this ik multiplication method, that is the Fourier method, the derivative computation is very accurate. Okay, so this is the power of spectral methods. Okay, now the time integration scheme is same. First take the forward Fourier transform of the initial condition, then solve the ODEs for the all the Fourier modes k, that is for one particular k is basically, this is the same as same computational complexity as the finite difference code. So this is the there you are fixing the x, and you are just solving for different x. Now you are solving for different k's. Now you have for different Fourier mode k, you have this ordinary differential equation of time, so that is why I have just written this as d dt, not del t. Okay, and your time advancement can be just using the forward Euler method. You can just use something else like RK2 or RK4 method also, and finally just take the inverse Fourier transform to get the solution in real space, and you are done. Hooray! So this is the simplest recipe for spectral method. First, from the initial condition, you have initial condition in your real space, just take Fourier transform, you will go to the spectral space. Then when you are in spectral space, then just solve the ordinary differential equation for different spectral modes. These K's are basically the spectral modes, okay, and then just integrate over time, evolve in time. Then after evolution in time, you just get your function in the real space back, okay. So just take a inverse Fourier transform to get back the real space function, okay. So this is what about the spectral method. Now let me implement it in my code. So just look at here that how it is I am writing, and in Fourier basis. So spectral means something very general, and I am doing Fourier basis, that is basically the sine cos or exponential of plus minus ikx basis. So these are complete basis, and you are solving in this basis. So as the functions, the basis functions are periodic, so you are actually taking the periodic boundary condition, okay, to solve this equation. So when we will do the periodic boundary condition, then you just use spectral methods, and actually not spectral methods, the Fourier spectral methods, okay. You can take different basis for the spectral analysis, okay. So it may be something else, some another transformation instead of Fourier transformation. Fourier transformation is the one of the special case. This is one of the case, that's all. So let me just start again with this function, that this is a Gaussian function, okay. So just take it like this. So up to here we have just solved the finite difference code. I'm doing in the same code because it will be easier to just overlap each plots from finite difference code and from the Fourier, the spectral code. They should match, okay, at least almost match. So let us see how. So this is my initial condition, then I need to go in the Fourier space. So this is uk is my Fourier transform of the u. So uk is equals to np, and in Python the numpy actually gives the first Fourier transform FFT. So and I will use the real Fourier transform, so real FFT RFFT of u. So it will be the uk is the Fourier transform of u now. So this is, that's it. So now you have to just solve it for different k modes, okay. Now for I in range, I am solving it for nt time steps, which is defined somewhere here, that is nt is equals to 100. Now you have to just solve it like this. uk for all uk is equals to uk plus dt, okay, so into 1 minus capital D into, okay. So now k square, how I will get my k? So here I have to just write k square, right? So k square. So for that, this FFT actually provide you the k also. So for the, in that case you have to just write it like this: 2 multiplied by pi, 2 pi. So 2 pi multiplied by the, these are the there is another inbuilt function that is called FFT fric. So it will give you the wave numbers. If you just multiply with 2 pi, it will give you the wave numbers, and depending on the grid size. So now I have to just call np dot fft dot RFFT freq. So as I am using this RFFT, so here also it is RFFT freq. For that, its first argument should be the number of points, and then the interval. So interval is basically, here my domain is basically, domain size is 2L and it is containing nx points. So the interval should be 2 multiplied by L divided by nx minus 1. So that's all. Now this is my, and this is, I don't require the, in the finite difference case I have to treat the boundary points individually and separate way, but here in Fourier basis your periodic boundary condition is already imposed because of the Fourier basis. So I'm not talking about anything here about the boundary condition. Now what is required, that I have to get back my solution in my real space. So for that I am just taking the inverse Fourier transform, that is, and p dot FFT r I FFT. So this will, IFFT means inverse Fourier first transform. Okay, so IFFT, it will give you the solution in real space. Now let me plot this u with x, so x comma u. Let me just do it with something else, some maybe star. Okay, and the color must maybe this color, let write green. Okay, green colored. Now my solution using the spectral method, it is ready. Let me run it. The Python and diffusion.py. So what is happening? Okay, so it is telling that IRF50 maybe, sorry, I think IRF50 it should be, and for that plot I need to plt.plot. Sorry. Now yeah, now this blue colored this curve is the initial condition, whatever I have taken as the initial condition, that Gaussian function e to the power minus x square, and this red one, this red curve is computed from the your finite difference code. Okay, and this green star is the spectral code. So hooray, you have the same result using the different method, and here I have also used the periodic boundary condition in finite difference method. So they are exactly same, so your code is correct. Okay, so instead of, if I just want to just implement it as Euler, instead of Euler I can use just RK2 method, let's say. So for that case you can just write it like this: UK mid, okay, UK mid is equals to this. So let just after dt by 2 time this will be the case. Now UK is equals to UK plus, not plus, minus capital D into dt into k square into UK mid. So that means your right hand side is now computed with this UK mid, that's all. So this UK is basically the previous UK, and this UK is the updated UK. So then it will give you the same answer, it must, and it is in RK2, the result will be better. Yeah, but here you cannot actually see the difference much because my dt is very much well resolved. Okay, so that's all. You can just expand it, modify this method to rk4 or any other higher order schemes, time integration, for time integration. But this is okay, rk2 is good enough to simulate this part. Okay, so thank you, and please subscribe and share if you like. Okay.